Okay, so it's time to start. So I'm the chairman of the session. We have 4 talks, and now I would like to introduce the first speaker, which is Hitch Marek, and the title of the talk is A Note of the Associativity of Functions Induced by Pair Orders. So please take the floor.
Thank you. Thank you for introducing myself. Good morning. The talk I'm going to present is the joint work with Andrea Zemankova, and it's a continuation of her previous work on pair orders and associativity functions. In the background, there is a transition from classical aggregation to pseudo aggregation, where commutativity condition is dropped out, and thus it matters the order of aggregated arguments. In order, it doesn't work, please. Okay, now it's work. Thanks. In order to get to the main idea what was solved, I would need to recall some results and notions. I'm going to consider binary functions. Idempotency and internality are defined over here. Every internal function is idempotent, but the converse need not be true. The main idea is the following theorem, which was proved for idempotent, commutative, and associative function. We are able to assign to it a relation, which is defined by the following expression that fxy is equal to x. Such a relation under these conditions forms a partial order. Moreover, partially ordered set with such relation is meet similarities, and the meet operation can be recovered as the values of these functions. So if we drop commutativity to arbitrary idempotent functions, we are able to define two relations in a similar way. Relation 1 is defined as by the same expression as in the theorem, and relation 2 is defined by fyx is equal to x. These two relations are said to be induced by the function f. There is an important there is important theorem that if we have idempotent and associative function, then this induced pair order forms the so-called induced pair of relation forms a pair order. Moreover, if this function is internal, then this pair order is linear. What does it mean to be pair order? It's a direct generalization of orders. Both are reflexive and transitive relations, which satisfy pair antisymmetry, which is generalization of antisymmetry conditions. But instead of one relation, both relations from the pair are present. We denote incomparability in standard way. Ni means the index of other relation in the pair, and Syx are the so-called projection groups. Maybe it's better to dub them as classes of equivalence. Why they are called quasi-orders, or by the lecture of Professor Debates, pre-orders? we are able to use classical Hasse diagrams, but instead of labels are not elements, but these projection groups. Finally, such pair order is linear if one order some elements are incomparable, then they must belong to the same class in the other order. If function f in the previous proposition is commutative, then we have the theorem on the previous slide. There can be shown that there is one-to-one correspondence between linear pair orders and idempotent associative internal functions. Some basic properties of pair orders are depicted here. If we consider two distinct elements, then if in one order x is less than or equal to y, then in other order it cannot happen that y is less than or equal to x, and similarly if y and x are in the same projection group, then in other relation they must be incomparable. If a pair order is linear, then such results are equivalencies. We have seen that behind the classical commutative case, there is a meet operation. So there is a pseudo-meet under this pair order situation, and we need to generalize the notion of meet. First of all, we need to generalize what does it mean a set of lower bounds, and what does it mean a supremum of such set. First we replace both relations. Then notions of dominance and strict dominance are used. Dominance is defined as an implication if A dominates C, if it holds that A is less than or equal to C for some order I, then it implies that C must be in the same projection group as A. Strict dominance is defined as follows. A strictly dominates C if C is less than or equal to A, but C is not in the same projection group as A. As I said, suprema is replaced by dominance, so we obtain the set S X Y. And finally, if we want to grasp the induced or relations, we obtain the set TXY. It will be in a few minutes clear what does these sets represent. Quickly recall the properties of dominance. If A strictly dominates C, that C cannot dominate A. If C does not dominate A, then A strictly dominates C. And finally, if A dominates C and C dominates A, then either they are in the same projection group or there must be incomparable in both pair orders. It can be shown that Txy is subset of Sxy, and this important lemma that if we consider associative idempotent function and induce pair order, then values of these functions are elements of set Txy. This inspired reverse definition how to a given pair order assign idempotent function such that what does it mean? It means exactly that values of such functions are elements of Txy sets. From this, it can be seen that if for some x and y, Txy is empty set, then there cannot be idempotent function which is induced by this pair order. And finally, there is a question, what are the conditions that leads to associativity of the induced function F? This question was previously solved by Andra Zemankova for on chains or for linear orders. And the condition is that if we consider a pair order on a chain, then there exists a monotone associative function if and only if there is a unique element in the set uxy such that it is in the interval of minimum and maximum of elements xy. And if such condition is met, then this induced function f is uniquely defined as elements of axy sign. Another important proposition is that whenever we have associative induced function to a pair order, then left and right monotonicity conditions are met for respective relation in pair order. So we see that conditions C1 and C2 are necessary if F is associative. The question was if they are also sufficient. Unfortunately, the answer is negative, but it will be in a couple of slides. First of all, not all induced functions satisfy these monotonicity conditions. We have this simple example. We have two orders. If we compute S and T sets, we obtain that S xy is defined by the following table. The set braces are dropped, so just to be clear, and it can be shown that such function does not satisfy condition C1, and thus it cannot be associative since monotonicity conditions are necessary. Okay. Here are some results. First, it was thought that these monotonicity conditions are sufficient for associativity because some results that were originally formulated for associative functions, it was possible to replace this associativity with these conditions C1 and C2. We have expression that comes in associativity. It belongs to the set S fxy and fyx. This, as a consequence of this, we have that if cardinality of sets Sxy is 1 for any x and y, then associativity is equivalent to conditions C1 and C2. The condition that for all x and y can be a little bit alleviated if we replace it with for such pairs that uv that are exactly fxy, fyx, which is present in the proposition above. Another result that was possible to replace associativity but monotonicity condition is the following. If we consider induced function for a given order pair which satisfy conditions C1 and C2 and two distinct elements x and y, and if we define elements A as fxy, B as fyx, C as fab, and D as fba, then the following holds that C is in S1b, B is at S2a, and D is S1a, and D is S2b. This also leads to the fact that function is associative for all elements, all triples, such as at least one pair is equal, containing two equal elements. There are equivalent conditions since relations, induced relations were defined functionally, we are able to replace this definition in a functional way. C1 and C2 can be rewritten as conditions D1 and D2. A condition that fxy is element of uxy is grasped by D3 and D4. Transitivity of pair order are rewritten as D5 and D6. All these conditions imply that fxy is element of sxy, and there is one-to-one correspondence between idempotent functions satisfying condition D1 and D6 and pair orders with induced idempotent functions satisfying monotonicity conditions C1 and C2. So in particular, 4 minutes, thanks. It will be quick. Yeah. If F, so in particular, if we consider idempotent associative function, idempotent function satisfying condition D1 and D6, then induced pair order, for an induced pair order, F is an induced function satisfying condition C1 and C2 and vice versa. We have counterexample that monotonicity conditions do not ensure that associativity. If we consider pair order, we are able to define sets S and T. Since set T consists of singleton, there is a unique idempotent function which is induced by this pair order. This function satisfies conditions C1 and C2, but unfortunately it is not associative as it is demonstrated here. If we consider this skip, and we have some condition of associativity. If we have induced function f and idempotent by a given pair order, and then associativity of order triple x by s is ensured if the following one of the following 5 conditions is satisfied. And we have also conditions of non-associativity. These are conditions that precludes that this induced function is associative. One of them is, for example, if x and xy are elements of this S, fxy, fyz element, and x is not equal to fxy, then f is not associative. And I just this. And this can be generalized to the functionally if we do not have function h, but this can be rewritten in the language of T and S sets. Okay, thank you for your attention. Here are some references.
Okay, thank you for your talk. And here we don't have much time, a lot of time for questions and comments, so very short question and very short answer. Yes, please, Bernard. This is the microphone. Don't hit.
I was wondering whether the property of associativity, you drop commutativity.
Yeah.
You have associativity. We have also a property that combines both, which has this two-dimensional thinking. It's bisymmetry.
Bisymmetry.
Are you familiar with bisymmetry?
Not really.
Bisymmetry is a property that has 4 variables. Think of a 2x2 matrix. If you aggregate first by rows, then by column, or the opposite, it should be the same.
Okay.
So in some structures, it's equivalent to commutativity plus associativity, otherwise not. But it has these 2 directions in it. So I was wondering whether that would not be a more natural or interesting framework for looking at these pair orders.
Thank you for the question. It's interesting, but we need to probably look at it in more detail.
Okay, the other question could be asked during the lunch. So thank you once more. And the next speaker, I am the next speaker, so I should share myself. So I need to prepare myself. Can you hear me with this? Okay, it's okay. So, because I don't want to thank myself for a nice talk too late, I need to prepare a timer. Okay. So the next talk, the title you can see, it's something related to topological entropy and dynamical systems. Basically, all results that we have that I'm going to present are done in cooperation with Jose Canovas. We, both of us, did our PhD in topological dynamics, which is a theory quite famous, I mean, quite decades old. And the basic model which we have here is the discrete dynamical system. Basically, it's a pair, x, phi, where x is usually a compact metric space and phi is a map from x to x. And when you apply the map iteratively, you have a state, you apply them iteratively, you obtain some iterations and movements. So this is the first iteration of phi f. This is the second iteration, this is the third iteration, and so on. Some time ago, we got interested in fuzzy dynamical systems because there was a nice paper by Peter Claren from 1982, who somehow introduced a reasonable model of fuzzy dynamical systems. We got interested in this model, so we started to study this from many points of view. So Claren came with the idea, okay, every state could be represented something like fuzzy state. And because we had some knowledge about the crisp map, we were interested what could be obtained for the fuzzy map. So just because this definition of this dynamical system is very simple, and the theory, the topological dynamics is still rich. I mean, the complexity arose from various conditions you can have here. The space S could be interval, Cantor set, unit cube, circle, topological graph, dendrite, many things can be here. 5, the map can be continuous, differentiable, piecewise continuous, piecewise differentiable, unimodal, and again, many options and the properties change substantially. For instance, here you can see just a small a picture showing how complex it could be even for simple maps, the interval maps. So maps which map interval 0, 1 into interval 0, 1. So what we did is basically that we started with Claren's model. We had many results. Many of them were related to topological entropy. I'm going to show them, some of them. Then we got interested in, because of one paper by Ethan Akin, who attracted us to the notion of fuzzy topological spaces, fuzzy continuous maps, and because also some fuzzy entropies were studied in this setting, we somehow tried to did some work in this direction, and it turned out that we are able to somehow connect both directions at some point, and that's basically what I'm going to show. So just to quick reminder, when we have compact metric space, the space Fx is the family of upper simultaneous fuzzy sets. F1x we consider normal fuzzy sets. F11x is the family of normal fuzzy numbers or fuzzy intervals. We also studied this space, but I'm not going to tell more about it in this talk. When we have this crisp non-fuzzy map, and we have this fuzzy extension because of the upper semi-continuity of maps, we have natural extension also to the set of non-empty compact subsets. As a map, we consider standard Zarek extension, and there are some nice relation between the map on the closed compact subsets and the fuzzy extensions on alpha cuts. And we considered some metrics that are considered as common in this model, namely the sendograph metric, endograph metric, and the level-wise metric, where we measure sublim of distances of alpha cuts. The topological entropy. What is topological entropy? This notion is not very common in this conference, so I have some pictures here. It's a notion that somehow describes the complexity of the dynamical system. So you can imagine that, for instance, those arrows represent the first thousands of iterations. So you have a system like this. The initial states are close to each other and they remain close to each other. But you can have some other system and those points go far away from each other at some point. So this is behind the definition of topological entropy, because you choose some distance, some number of iterations, and you want to compute all points that go epsilon far within the first n iterations. And we will get so-called epsilon separated pair. And if the system has many such points, such pairs, then we naturally the system is more complex. So we somehow compute them. We have the cardinality of all epsilon separated sets. We did some computation, and this is the definition of the topological entropy. Of course, this is not the only definition. There are many definitions which are usually equivalent on compact metric spaces, but don't have to be equivalent always. In all cases, we can use finite open covers of the space, did some computation, and so on, and we obtain another topological entropy. We can also start with finite partitions of measurable sets. We do some computation, and we again have so-called metric entropy. The properties are that we can, by this computation, we can obtain a number 0, finite number, or infinity. If we have the topological entropy is equal to 0, then we say that the system is non-chaotic. If it is positive, it's chaotic, and the higher the number is, then the more chaotic the system is. So, for instance, if you consider the map on the interval 0, 1, which map sends x to the x square, everybody can imagine this map, then this is very nice, simple map. It has zero topological entropy. If we consider a tenth map, which has a graph here, because the graph looks like a tenth, then the topological entropy is the logarithm of 2. This is the second iteration of the tenth map. It's called set map. Do you know why? Because there are 2 tenths. And this is the third iteration of the tenth map, and the topological entropy is 3 times logarithm of 2. This is the topological entropy of this is 2 times logarithm of 2. Okay, definitely if we go from crisp to the set valued or the fuzzy extension, we gain more and more complexity. And because not all systems, fuzzy systems are follow, we start with compact set, need not be compact. We need to consider some definition on the non-compact space. So if the system of fuzzy set is not compact, we just take supremum of topological entropies taken on all compact subsystems. Okay. And one of our results is this one, that under some very easy to satisfy conditions, we have 0 topological entropy of the crisp map and infinite topological entropy of the fuzzy extension, if we consider the general case. Those conditions are very easy to satisfy. For instance, when we consider this map on the interval 0, 1, the x is mapped to x squared, and even this map satisfies this condition. So it looks like the notion of topological entropy for fuzzy systems is completely useless because we immediately obtain something very complex. How is it possible? This is just you can imagine how it works, because you have system consisting of those black and red points. So it's countable system. 0 is mapped to 0, 1 is mapped to 1, and every black point is mapped to its neighbor on the left side, the closest number. So all the black points are moving towards 0 and leaving somehow 1. So you can take a subset of points here. They are always close to each other. You get something around 0 after finitely many iterations, and they are far from each other. So this is the way how you ensure that there are many, say, an epsilon separated sets. So, and basically, this is the idea how everything works. So, because we had some suspicion that, okay, that the notion of topological entropy is useless for fuzzy systems, we restrict our attention to something nicer. We had some knowledge about the space, which is interval 0, 1, which is well studied, but still complex. And we considered the direct extension on the space of fuzzy numbers or fuzzy intervals. And we proved that when we considered our three metrics, then we have the equality. So this is the nice property. And it would be nice if this would be valid in general. But that's not true, because there are some complex spaces in the plane called dendrites that just are the counterexample. But this property, this equality, doesn't hold only for intervals, but for many other spaces. It was generalized later by some Chinese guys. Okay, that's the first direction. The second direction, fuzzy topological spaces. This is the standard Chang's definition of fuzzy topological space. When we have this fuzzy topological space, we can have this fuzzy continuous map. And recently we found an archive article by Ethan Akin, and he had some discussion with Sasha Shostak. Okay, what should be the first axiom in this definition? And he discussed several options that every constant function should be a part of this axiom. And he also said that this topology should be closed under positive affine transformations, which is this property. And this way we obtain affine invariant fuzzy topology. So instead of this condition, we consider this affine invariance. And he also somehow discussed relation between crisp and fuzzy topology. So when we start with topology on X, he considered the fuzzy topology omega tau, which is given by the set of all lower continuous functions. And when he started from fuzzy topology tau f, he considered the iota tau f as the coarsest topology in X, such that every element of tau f is continuous. And there was some discussion about this, and not only concerning the axioms of fuzzy topology, but also concerning what should be the notion of compactness. Because there are several ways how the compactness can be defined. For instance, fuzzy compactness can be defined as every fuzzy cover has finite subcover. And we also work with the notion of fuzzy compactness when the condition is the same, but the finite subcover should be defined for every a minus epsilon for every epsilon. And Ethan Akin, basically, he wrote several books, papers in topological dynamics, and this is the only paper which he wrote for, say, fuzzy mathematics. And we agreed with his arguments, and he strongly recommended to work with affine invariant topological spaces and with this notion of L-fuzzy compactness. And we somehow elaborated somehow work with the definition of topological entropy by Adler, because you find we somehow work with finite open cover, did some computation. For non-compact space, you worked with supremum of topological entropies on compact subsystems. Here we now, not only us, but there were some mathematicians who replaced this notion of finite open cover by fuzzy open cover. did some computation to find the notion. We denote this notion by HF. For non-fuzzy compact, again, we take supremum of some entropies of subsystems. This is for fuzzy compact spaces, and we work with this notion of L-fuzzy compact, and we did basically the same, but I mean the assumptions are different. So HLFF is defined this way. It can be shown that the definition is correct, that for non-L-fuzzy compact space, we can have something different. Again, take supremum of topological entropies of subsystems, L compact subsystems. And what we have, okay, we have more results. So usually let's get attention on the red. So when we started from compact topological space, we have this topological entropy that agrees with if we restrict our attention on L compact subsystems. Okay. Thank you. Thank you, myself. Okay, but when we work, maybe have compact normal topological space and we start with only fuzzy compactness, we always obtain 0, which is, I mean, a nonsense. When we start with fuzzy compact sets with topology which is affine invariant, we again obtain 0 in any case. And when we start with L fuzzy compact set with tau f affine invariant, we have the equality. So, and again, the notion of affine invariance is crucial here. Without this, many counterexamples can be found. I mean, this affine invariance is important on its own because Ethan Akin presented several really strange phenomena which are present if you don't consider affine invariant fuzzy topology. For instance, in some cases, only constant functions can be continuous. So which is not the case that we usually want. Okay, following this direction, we again found something more for fuzzy intervals, for the unit interval. So in both directions, in the Claude model, in the model of fuzzy topological spaces, we showed something, and again we found something that is valid for interval because interval is the case that is most studied. And there were some, however, those two directions are inconsistent in general, because I had a counterexample on the dendrite. So we had some observation, and the observation is that when you consider the system of fuzzy points, which are, say, constant times characteristic function of a singleton, which is not, I mean, this system of fuzzy sets is not interested. Nobody's using this, but this is the boundary between those two directions. So if we consider the system of fuzzy points, which is denoted by XF, we define the entropy on the space of fuzzy points. We can again start with compact matrix space, and we show that under some preparation, we have all the equalities, even including those metrics that I mentioned at the beginning. And we can do this again, start from the fuzzy setting, define something crisp, and again, we have the equality. So, I mean, the system of fuzzy points is really the meeting point of this. It's not very interesting, but okay, we have it. Analogy, we can do this for the non-compact case. So what we did, that we just somehow developed the clearance directions, somehow developed the direction of fuzzy topological spaces. In both cases, we work with topological entropy. We have some general results, and what is our finding that the system of fuzzy points is the somehow intersection of those directions. And in the case of we want to work with fuzzy topologies, fuzzy entropy, that we always should work with all fuzzy compact spaces and affine invariant topologies. So that's all. Thank you for your attention. Okay, and are there some questions? There are some questions. Thank you.
I'm confused by the notion topological entropy because it's based on some distance or metric, and we usually speak of topology when we don't have anything more like this. So it sounds strange.
No, if there is a metric, we can find those n epsilon separated pairs. If there is no metric, we can start with this for the open partition or open partition. It was shown that for compact metric spaces, I mean, those two notions coincide.
I have a question about the use of the extension principle,
But what?
the use of the extension principle. At what point is its use here? I couldn't really figure out. Can it lead to inflation? Like normally, if you have an uncertainty about the initial condition, then you should individually propagate, follow the trajectories. But here it seems that the map is applied each time.
Yes, yes.
So then it explodes.
It could very easily explode. Yes.
And is there a way to counter that? I'm thinking of the Lyapunov exponent, which is another way of measuring, on which I've done quite a lot of work. There you trace the individual trajectories to see if you have infinitesimal changes. How does it influence? Is that a possible approach here?
At least I don't know, but I agree with your comment. I mean, at some cases, at some points, I mean, this could. I mean, the general situation is that I mean the map increases the starting fuzzy state increases immediately and almost a huge part of the space. So there should be some instrument which could somehow decrease it. That you can trace the core, keep some fuzziness, but it's So
that might be the reason why these results diverge.
Yeah. So I think that there should be some time-dependent extension or something like this that will handle with this. Yeah, I was thinking about this, but I have no answer, no general solution. Not enough microphones.
I would expect it when you speak about fuzzy dynamic systems that you first define the fuzzy metric topology, because for example, for your first picture, you have like a fuzzy open balls, and then you forget about them. And also, if you first understand in which fuzzy metric space you are working, then the compactness can be extracted by themselves, like automatically, from the understanding of fuzzy metric space.
Yeah, I just realized how much time we have. So maybe can we discuss this later?
Yes, okay.
Because there should be. I'm sorry for this. I just tried to answer. I didn't follow the time. Yeah, can we?
Okay.
Yeah, sorry for that. So there is not enough time for the discussion. I will keep it for lunch. And now we can invite the third speaker. And the third speaker is Dimuro Grakalis, and the title is Capturing Temporal Interrelationships Among Data by Choquette-like Integrals, Application to Network Traffic Forecasting. Quite long enough to handle with the microphone. 20 minutes.
Okay, let's start this presentation. That is, it's initial work on the development of models based on Choquette integrals to network traffic prediction. Okay, and this is these are the colleagues that are working in this subject. Some of them in the application area. Okay, so let's say some motivation under this work. We start working this project when my colleague Bruno Dalmaso came to my office, an prediction, and then he started to explain me his challenge in his work. Okay, so the next generation of network paradigms, like Internet of Things, has completely changed the way the networks are designed and managed. Since the number of connected devices continues to exponentially. There are so many problems of to maintain safe and reliable connectivity. As a consequence, networks, you know, are very popular targets for cyber attacks, many of which can be identified by examining traffic patterns. So a key tactic to reduce those risks is anomaly detection, which seeks to stop deviations from typical behavior before they can cause serious problems in the network. So Bruno Dalmaso explained me that conventional methods frequently depends on statistical or machine learning techniques, but their use in dynamic situation is limited because they require a large amount of historic data or prior training. Additionally, those methods may be not effectively when we have highly unstable environments like IoT scenarios, where the relationships between time series observations can reduce rapidly, fast in time. Then Bruno searched for aggregation operators in the literature, and he found that he couldn't find aggregation operators that consider aspects that the last observed values, the most recent, are more significant than the others. And aggregation that consider the existence of intemporal relationship among data. Then we start to collaborate, trying to propose an initial concept of temporal capacities, and with this concept to define temporal Choquet integral and temporal CF integral. Those functions are increasing, directional increasing functions, sometimes increasing, but directional increasing functions that consider the desired temporal relationship among data, giving priority for the most recent data in observed slide windows, because they work with slide windows in the time series, okay? So for each window, there is a most recent data, and then this most recent data must be given a priority. So the obtained model considers the macro tendency of the data, accounting for the time series suitable order within a slide window. Then we first our comparison with the Poisson moving average, that is a standard method using in this context. So let's see some notation, okay? So the first, we denote by this tuple D, a temporal series of network data flow related to a time set T, okay? This is the time series related to the data flow. A key concept in this work is the concept of time window. And a time window then is a subtuple, okay, in the time set. Of course, the times here are consecutive, but like this, okay? And the current observation time is the last one, is the highest time, okay? And by convention, theoretical convention, of course, the empty set is a time window of size 0, okay? So this is the notation of the set of time windows, and this is the data flow associated with a time window. Then the concept of a sub-window in a time window is a sub-window in a time window is then a subtuple of the window, okay? So if you have a window, you can make the window slide windows, and then to have sub-windows, okay? And here the set of observation times related to sub-windows. Of course, this is the size of a sub-window. And then let's recall the concept of a capacity. that is a grounded set function, and that is increasing, okay? And a temporal capacity is a grounded set function, okay? With the characteristic that it satisfies a condition that you call temporal increasiness. So for each two sub-windows here, okay, the temporal capacity nu of the first sub-window is less than the temporal capacity of the second sub-window, if and only if the sum of the times of the first is less than the sum of the times contained in the second sub-window, okay? This is the key concept here that capture the idea of if you have more recent times, you have to increase the value of the temporal capacity. Of examples here, some examples of temporal capacity, 3 examples, nu1, nu2, nu3. It's very easy to see that they satisfy the condition of temporal increasing. And here, all these temporal capacities are also increasing, are temporal increasing, but are also increasing, okay? But temporal capacities may not be increasing. Let's see, for example, this one, nu4, defined like this, okay? You have defined in case, and you have different case when k is even or odd. And then considering this window of size 10 here, it follows that if you consider 2 sub-windows, this one, and you calculate nu4 for this first, you have this value, 35, and nu4 for this first one, 14. It's immediate that they are temporal increasing, but they are not increasing. So they are temporal capacities, but they are not capacities, okay? Those temporal capacities are also increasing, but sometimes you have another that is maybe not increasing. So you see that each increasing temporal capacity is a capacity, but the conversion does not roll, okay? Take, for example, this very simple capacity, the cardinal capacity, okay? That gives only just the cardinality of the sub-window. And it's easy to see that this capacity is not a temporal capacity. It does not satisfy the condition of temporal increasing, okay? So given this sub-window here, this window and 2 sub-windows, this one with size 3 and this another one, they have the same size, okay? And you see that if you sum the times of the first, you obtain 6, and if you sum the times of the second, you obtain 25. But here, considering the cardinality, they are equal, okay? So they are not temporal increasing. Then some properties, initial properties, because this is the initial work. If a capacity is symmetric, maxitive or minimative, then it's not temporal. The set of temporal capacity is closed under the arithmetic mean, weighted arithmetic mean, convex sum, okay? It's closed, also closed under the conjugate whenever it exists. And if you consider, well, here, if you consider a strictly increasing function whole with this property, then this function is also a temporal capacity, okay? So there's some properties, initial properties that we have checked. And of course, you may ask for the additive property. So what we have checked that there exist additive capacities that are not temporal capacities, as for example, the cardinality. Exception before that it's not a temporal increasing. And there are several temporal capacities that are additive, like for example, the three first examples, okay? But there are also temporal capacities that are clearly not additive, like this mu 4. So we don't have any conclusion about the additivity of temporal capacities. Then we use the concept of temporal capacities to define a Choquet-like integral based on that we call temporal Choquet integral, okay? So let's see this concept. You consider a network data flow here related to a time window and a temporal capacity. So we define this function. The input are the values of the data flow, okay? It looks like a Choquet integral, but here you have this concept here that you see how you made this, okay? Of course, the input is ordered increasingly and increasing permutation. And this set is a set of observation times of the largest components associated to the data flow, okay? And then this is a sub-window composed of the observation times of this set A here, ordered increasingly, okay? So this is a temporal Choquet integral. And of course, we tried to generalize this concept in order to have more flexibility for the applications. Then we substitute the product operation by a function f here, okay? Just a function f that may be assume any value, any function that we know, T-norms, overlap functions, okay? Any pseudo-overlap functions. We don't have to have any special property here, okay? Of course, when looking for properties, you have to add additional properties for this function. But for to be well-defined, it's okay. Now, some properties, initial properties that we have checked, okay? Every temporal Choquet integral is increasing. Every temporal Choquet integral with respect to a normalized temporal capacity is idempotent. Then if the function f is directional increasing in the direction of the vector 1, 0, then the corresponding temporal Choquet, SCF Choquet integral is also directional increasing in the direction of this vector A. Okay? So it is directional increasing. Some kind of increasiness we can this integral we can give to this integral. And this is the condition of the temporal CF integral to be idempotent. Okay? So of course we don't have a lot of properties because it's just an initial work to see if they behave well in the applications. And then the application was done by Bruno Dalmasso and his students, okay? And then they applied those temporal Choquet-based integrals that were designed to give priority to recent data and to capture some temporal relationship within slide windows for a network traffic prediction. And this is the methodology they proposed, okay? It's composed of 5 steps from the data treatment. 3 minutes? Okay. And then, so I'm finishing, okay? So we performed a comparative analysis involving 17 distinct equations, because you can substitute the functions in the definition. For example, the product norm, Lukshayev's norm, Hamark, and some overlap functions, okay, pseudo overlap function like this, and try the experiment using real data. Interesting to see that, for example, the two best ones is the one using this function, that is a pre or pseudo overlap function, but the behavior are different according to the size of the window, okay? For example, of smaller size of windows, this temporal integral behaved better because the error is not high, but for larger, the Poisson move operation, the standard one, is better. So the conclusion, and then thank you very much. This is the group of investigation. Okay.
Thank you very much for your talk. And we have time for short question. Okay, can you briefly explain your further directions? Your further directions. Do you somehow plan to continue?
Yes, you have further work, okay, but some new methodologies, and we have other publications about this subject, but also using we are now using the inspired Choquet integral that Javier talked in the first talk.
Okay. Okay.
This is the first part of the work you have to leave out.
Okay, good luck with this. So thank you once more. And the last speaker of the session is Varfolomieva Ksenia. I hope that I pronounced this correctly. And the title of her talk is on the behavior of morphological operators on the morphisms in the category of alpha Z with a structuring element. So take the floor.
Good morning. Thank you for introduction. And this is a joint work with the Professor Ingrid Uljan as a part of my PhD work in progress. So before coming straight to results and the context of our work, let me introduce in briefly mathematical morphology context in which we are working. The field arose in 1964, and in the beginning was used on binary objects, but in time developed in fuzzy sets as well. And nowadays mostly used for image processing, signal processing, helping highlight some objects, reduce noise, make quality better, and so on. And the classic mathematical morphology mainly based on translation operator, where in dilation operator makes it the given set bigger, in erosion operator makes a given set smaller, and also there is a role of structural element which is commonly smaller than the main set and usually well structured. Like here is a simple example of the original structure, which is white dots. And here's basically structural elements like a square of also white pixels. And you can see that in dilation case, it is like the bigger structure, and erosion smaller. So there are also so-called smoothing operators, the root operators, opening and closing, obtained by excessive application of dilation and erosion in case of closing, and erosion dilation in place of opening, where the second application is with -s, which is quite helpful in case of not symmetrical structuring elements. And as we can see, the final structure resembles the original one pretty well. in both closing, opening. And of course, there is a Galois connection or a junction between morphological operator, which plays quite a big role. So, getting to our framework of our research, there are, with a bit of moderation, there are works of studying morphological operators in morphological spaces or morphological operator structure in linear spaces, but then not many works, as far as we know, about studying morphological operator behavior under morphisms of spaces. So to do so, we prepare basis for it, firstly taking additive groups with satisfying following axioms and homomorphism between these additive groups. So here, then with the morphisms acting as morphisms, with homomorphisms acting as morphisms, we denote a category, the first category here of additive group, where these additive groups are objects and described mappings are morphisms. Here is the right moment to go to fuzzy mathematical morphology, like taking the classical definition, reconstructing it in verbal construction. We smoothly go to one of the commonly used definition introduced by Professor Debaets and co-authors, where in case of dilation, there is a minimum T norm, and in case of erosion, there is a residuum, which is related to minimum T norm in the sense that Galois connection between them fulfilled. So, moving forward to the framework of our base, it was colored. It's a pity that it's not colored anymore, but still, the schema remains, and we move to L-power sets with inner sets with structuring elements. So we prefix structuring elements because it is also like one of motivation to get the role of structuring element, because in many works, when it comes to study, the role of structuring elements usually diminish. Here we wanted to preserve it in order to study it forward, actually give some additional benefits in practical application, because it helps to regulate the results, so to say. So we had these additive groups, group homomorphisms, now coming further to L-power sets and spaces with L-power set spaces with structuring elements. We also introduce this image and pre-image operators obtained by Zada extension principle. So in the case, in our case, these are the mappings of our L-fuzzy homomorphisms. These are our L-fuzzy homomorphisms, and what is important that there are also connection that should be fulfilled for the structuring elements, as you can see for going to one side or one way and another and backwards. So we had additive structures, homomorphisms. Now it's spaces with structuring elements and image pre-image operator with a special notion to structuring elements. And having all of this, putting it all together, we have spaces with structuring elements, as I said, serving as an object. Morphisms, image operator of morphisms serving as morphism with a special notion to structuring elements, which constitute like image category, so to call. And the second case, when it is a pre-image operator, denotes pre-image category. And in order to be convenient to work further, we put morphisms together and denote a category as a set with the same sets with structuring elements and image and pre-image operators as morphisms. Having this basis, here is the final basis as we have it. We can move forward to behavior of morphological operators in this category. So reminding dilation definition first, and by varying the main image, we have this dilation operator working on lattice, and I call dilation operator on the corresponding output set of our space. And here with the morphisms from the constituted category and with the notion to structure elements fulfilled, we get this connection, this inequality. Furthermore, for the morphisms where corresponding mapping of additive groups is subjective, we get the equality. So now for the pre-images with the special notion to structuring elements, we have this kind of inequality, and again, when the initial mapping is subjective, this is quality. Moving further to erosion, and taking into account that erosion in its definition has residuum, which is be challenging to work with during behavior study. The results slightly alters. So for the first of all, the pre-image, which allows to work a bit more freely, but still the corresponding initial morphism is need to be subjective in order to obtain the inequality, and moreover, we need structural element to be even more strictly equal in order to obtain the result of quality. And in case of image, we ask for structuring elements to be equal. We ask for subjectiveness in order to obtain results for behavior. Moving to derivative operators of opening and closing, with the small reminding of definition in fuzzy case, it's like this, using dilation erosion. We actually can, first of all, interpret it already obtained result in diagram, where the highlighted parts of diagrams are those bigger parts of inequality showed before. So in case of opening, it works like that. And if we speak about morphisms from the category described, we ask already, as we already asked before, for structuring elements to be like corresponding to each other, to equal, and only then we can obtain this inequality in respect to opening operator. Moving forward with the closing operator, same, but in the beginning it's dilation but and erosion. We can interpret it, the result we get before with such diagram, where again highlighted the bigger parts, and the result for closing operator is the following, again asking for all the structuring elements to be equal in that sense. And yeah, the literature, and that's it. Thank you for your attention.
Okay, thank you. Are there some questions? No.
Only a small technical comment. At your starting slide, probably 2 or 3, could you switch it? At your starting slide, probably number 2 or 3, where you define the homomorphisms, there was something I didn't understand, really. Further. Was at the beginning.
Slide 3, right?
2 or yeah,
Definitely
you
not
are
3.
15, so we have to go at the beginning further. Now here. What does mean lambda? Because you are in additive groups, so there's no possibility to get such a condition.
Like
That's for vector spaces and so on, but you are in groups.
Yeah, maybe it is something that's made from the moment when we started with linear sets. Yeah. Thank you for your comments.
Okay, some other questions, comments?
Can you somehow summarize your results? Can you say what they are about or what consequences follow from your results?
Well, besides having fun studying morphological behavior, I would say that these results like help to let me move to the slide. Help to understand the way it works, and maybe it is worth trying. It's a bit more practical, like studying in on some with some operators like subtraction and so on. But first of all, yeah, it helps to understand the way the structure of a morphological operator works. It gives us a chance to work with between different contexts. I hope that was some.
Okay, thank you. Oh, maybe Bernard?
Maybe shorter, but not easy question. So closure and opening operators, they can be also described in terms of properties. So is there any result that allows you to say that a closure operator or opening operator is good because it can be decomposed as a composition? Is there any result in that direction that tells you, can you find erosion and dilation that give that operation?
Not yet. I think we were thinking about it like in the beginning started, but then moved to this direction. Yeah.
I mean in literature in general.
In general, maybe not something that we faced. That we definitely not something we was using, not something we saw.
Okay, one more question. Okay, if not, let's thank the speaker once more. And I'm closing the session because it's lunchtime. So enjoy.